we're going to talk about some word problems involving linear equations. So we already know how to solve linear equations from the last section. And so now we'll talk about a few like common sort of problems that you would solve that involve those types of equations. All right, so let's just first look at the first example. We have a 60-foot piece of rope cut into 3 pieces. And all we know is that the second piece must be 1 foot shorter in length than twice the first piece. And the third piece must be 10 feet longer than 3 times the length of the second piece. Right? The question is, how long should the longest piece be? All right, so the first time you see it, it could just be coming out jumbled and confusing. But what we first have to do is identify a variable. What is it that we don't know and that we would like to know, right? And what we don't know, for instance, is the length of the first piece. That's a good starting point. All right, let me put the light on real quick. Hold on one sec. There we go. All right, that's better. Okay, so let's let x be the length of the first piece. Then we have to interpret these pieces of information to get the lengths of the other 2 pieces in terms of that variable, and then we can add those up and get 60. All right, so what we know, the second piece must be 1 foot shorter in length than twice the first piece. Well, if x is the length of the first piece, then twice its length is 2x. 1 foot less than that is 2x minus 1. So we know the length of the second piece. For the third piece, we know that it is 10 feet longer, so we're going to add 10 to something. Then 3 times, we're going to multiply something times 3, the length of the second piece, not the first piece, but the second piece. We just wrote its length down to be 2x minus 1. And so we're going to multiply 3 times 2x minus 1 plus 10. That expression represents the length of the third piece. All right, so now we have the lengths of these 3 pieces of rope. All right, so just imagine that you had cut it into 3 pieces, right? 1, 2, and 3. We know the sum of these lengths must be 60 feet. And so we get the equation, the sum of those 3 lengths is 60. All we have to do now is solve this equation and determine what x is. Well, to solve that, we have to simplify the left-hand side. So we're going to distribute the 3 through this guy, add the x terms up to get 9x, and then add the constant terms up to get 6. That's equal to 60. And so now subtract the 6 from both sides and then divide by 9. That gives x equal to 6 feet. And so the length of the first piece is 6 feet. Then just plug these in. Put x equal to 6 in here to get that the second piece is 11 feet, and put it in here to get that the third piece, if you simplify this with x equal to 6 in there, you'll get 43 feet. Right? And so the length of the longest piece of rope in this situation is 43 feet. All right, so the key here, when you read through the problem, read through a couple times just to make sure you have the lay of land in terms of what it is saying. Then identify a variable, let's call it x, let's say, whatever letter you want, call it x, and then use the information in the problem to express other quantities in terms of x. Get an equation that's linear, solve like you did last chapter or in the last section, and then answer the problem that's being asked. All right, that's the general approach. All right, let's take a look at, let's see, I'll let you read example 2. Let's look at example 3. All right, so we have at Zide's Sport Shop, we have a canister of tennis balls that cost $3.50 and a canister of other types of tennis balls that cost $2.75. And the high school tennis coach bought canisters of both types of balls, and he spent exactly $40.25 before tax. So we don't know how many of each type of ball he bought, but what we do know is that he bought 1 more canister of Penn balls than he did Wilson balls. Right? So we know the relationship between the number of each canisters that he bought, and we also know the price of each price of one of each canisters, and we know the total he spent. So somehow using that information, we have to generate a linear equation that can be solved to answer the problem, to answer the question. All right, so why don't we just let X, we have to identify a variable. Let's let X be the number of canisters of Wilson balls. Then what we know here is that he bought one more can of Penn balls than he did Wilson. So the number of Penn balls is X plus 1. Notice we don't know either of these, but we do know how they're related. And they're both in terms of the same variable. That's important. Okay, so now what we want to do is find what X is. Well, to do that, we have to use the other information in the problem, namely the cost of each canister of, or per brand, and the total he spent. Well, if he bought X canisters of Wilson balls and each canister cost $3.50, then apparently the amount he spent on X canisters of that type of ball has to be $3.50 times X. All right, so that's what I'm summarizing here. Kind of helps off sometimes to make a table just to kind of gather the information. So the number of canisters bought times price per canister is the cost for that type of tennis ball. Same thing for Penn. He had X plus 1 of those guys. Multiply that by the price per canister. So this expression here is the number of dollars he spent buying X plus 1 canisters of Penn balls. And we know the total bill was $40.25, right? And so what you'll do is you'll add these two costs here, right? So 350X plus 275X plus 1, that sum has to be $40.25. And lo and behold, that is a linear equation that you can solve for X to answer the question posed in the problem. So to that end, if you simplify the left-hand side, you get 625X plus 275. That sum has to be $40.25. So what do? You subtract the constant from both sides and then divide by the coefficient of X. If you do that, it works out nicely. You get X equal to 6. And so he bought, remember X is the number of canisters of Wilson balls. He bought 6 of those guys, and so he must have bought 7 of the Penn balls. Okay. All right. Example 4 is not difficult, but it's one of those that comes up a lot in a lot of different settings when you talk about percentages, markdown, markup, that sort of thing. And so let's just look at this. A little bit dated in the sense that Kmart I don't even think exists anymore, let alone a blue light special. But you know, despite the anachronistic phrasing, it has meaning. All right, so suppose Mr. Coffee is on sale for $23.40, and the price of the coffee maker, given that it's a blue light special, they marked it down 30%. Right, so the $23.40 is 30% of the original price, whatever that happens to be. And what we're trying to do is find the original price. Okay, so if we're trying to find that, what we're trying to find is either the variable or it's somehow related to it. So in this case, let's let X equal the original price of this Mr. Coffee and see if we can't find an equation that can be solved to find it. Okay, so what we'll do, we know that if that's the original price and the given price here is 30% marked down, then what we would do is subtract 30% of that cost from that cost to get the $23.40, right? So this expression on the left-hand side, what this means is the original price minus 30% of that price. This will result in a 30% markdown. All right. Look, that's a linear equation, right? So it can't pop out any quicker than that. Simplify the left-hand side to get 0.7x. The right side's already just a constant. So now if you divide both sides by 0.7, you get that X is approximately 33.43. And so the original price of Mr. Coffee is 33.43. All right. All right. I'll let you read this one. This one is very similar in nature to the cost problem that we looked at. When you read this example, I want you to pay close attention to that, because oftentimes what happens in algebra courses is that two word problems look very different. One involves cost and one involves a percentage of chemicals being used. but in fact, they're basically the same thing. They're the same type of problem. So I want you to look at this problem, read through the solution, and then really compare it to example 3, just to see what I'm saying in terms of structure. They really are solved in exactly the same way by identifying the cost of canisters of balls to percentages of certain types of nutrient solution. All right, so take a look at that on your own time. All right, and let's look at this one. So I want to talk kind of generally about distance equals rate times time problems, because they always cause people heartburn, right? So this is important to remember, right? So if you were to run 10, no, not 10 miles an hour, you have to be a cheetah to do that. If you ran 4.5 miles per hour and you ran for 2 hours, then the distance you traveled would be the amount of time you ran times your speed, which is 4.5 times 2, right? So you get 9 miles. So this makes sense. It's something that you bump into a lot. What you often, or what students often overlook, is that you can rearrange these terms, right? I can divide both sides by the rate and get an expression for time in terms of distance and rate, or I can divide both sides by time and get an expression for the rate, right? And each of those manipulations of this formula are handy depending on what problem you're trying to solve. All right, so let's look at this one. You have, how long does it take a girl jogging at 17 miles an hour? Again, no one in their right mind can jog that fast. Let's just assume that she has, maybe this is I don't know, a cheetah or somebody with bionic legs, because there's no way you can run that fast. But anyway, let's just, for the sake of argument, let's assume it is. To overtake her instructor walking at 7 miles an hour, which again is a sprinting pace. So it's kind of funny. But assume that the instructor had a 3-hour head start. Okay, so let's look at this. We hit the instructor has been walking at that rate for 3 hours. The minute those 3 hours are up, this girl starts to sprint at 17 miles an hour in the same exact path of her instructor. All right, and so let's look at this. What are we trying to find? Let's let X be the number of hours this girl has been running when she intercepts her instructor. So the minute she comes right up by her instructor, we'll call that time that she's been running X. All right, so given that, since the instructor had a 3-hour head start, he or she would be walking for X plus 3 hours, right? So walking for the 3 hours initially, plus the amount of time it takes that girl to catch up to him or her. All right, so let's actually label all the information that we know and see what we can do. This will have the rate, time, and distance for the girl, and the rate, time, and distance for the instructor. The rate of the girl is 17 miles an hour. The time the girl is running when she actually meets up with the instructor is X. So how far has she run? Well, distance equals rate times time. And so you get 17 times X. She's run 17X miles at that point. Similarly, the rate of the instructor is 7 miles an hour. And the time the instructor has been walking when the girl actually meets him or her is X plus 3, or 3 plus X hours. And so the distance traveled is the product of those two, namely 7 times 3 plus X. But now think, all we need is the distances, right? Because we know that we're interested in the time where the girl intercepts the instructor, which means their distances traveled have to be exactly the same because they're traveling along the same path. All right, and so we get 17X, that's the distance the girl has traveled, equals the distance the instructor traveled, namely that expression. Again, that's a linear equation. So you distribute the 7 to both terms on the right side, take the 7X over to the left, and divide by the coefficient of X to get X equals 2.1. So what that tells you is that at these crazy rates, it would take the girl 2.1 hours, which is equal to 2 hours and 6 minutes, to overtake the instructor. All right, here I summarize that method of attack that I had just mentioned verbally in a previous problem or two. So just kind of keep this attack in mind when you're trying the problems out for the homework. Again, take a look at that supplementary video list. That'll be helpful. It gives you other types of problems beyond what I talked about here, just to give you a full sort of sampling of what kind of problems arise when trying to solve linear equations. All right, very good. Let me know how that goes.